This is the second video in a series of videos in which I shall attempt in real time to solve questions from this book called Problem Solving Strategies. And one of the strategies they call the invariance principle, where basically to solve a problem you try to find some interesting quantity that either stays constant or behaves in some way. For example, it might be an integer quantity that decreases, in which case you know that some process has to terminate, that kind of thing. So typically there's some process that is going on, and you identify the quantity that informs you about whether the process must terminate, what happens if it does terminate, and that kind of thing, what properties must be preserved as you go along. Last time I just did it trying to sort of use my wits, but this time, having had the practice from last time where I did 6 problems, I want to try to be more systematic if I possibly can. I don't know how easy that's going to be. Last time 3 of them I'd seen before. This time I haven't seen any of them before. I also don't know how long this series is going to be, because rather terrifyingly the book has 60 problems just on this topic. I don't think I'm going to make... So I did 6 in about an hour. I don't think I can make 10 hours of videos just devoted to this one problem-solving technique. But not also. I want to sort of carry on until it ceases to seem being useful or interesting to me. And as I say, if it's of interest to anyone else, then that's just a nice bonus. But really, actually, I must come clean and say that one of my main reasons for being interested in this is that I'm very interested in automatic theorem proving, and so at the back of my mind is the thought of how would a computer, in principle, be able to come up with these invariants? What sort of search process would it need to have put into it? And is there something that could be done that's not sort of too much just giving it a list of invariants to look for and do a brute force search amongst those invariants? Although I think I will do a certain amount of that, actually, because I do have a rather small repertoire of obvious things to try, like parity type invariants, and also sums of squares, and also sums of various integers that might be associated with a problem, those kinds of things. So without further ado, let me... oops, I forgot to prepare to share my screen properly, but here we go. So let's get a nice new, that's something else, nice fresh sheet, and I will open up the book and see what question 7 was on the list. That's another one about white, black and red chips. So it says there are A white, B black, and C red chips on the table. In one step you may choose 2 chips of different colors, and I presume you're going to replace them by something, and replace each one by a chip of the 3rd color. So if you watched the previous video, this is similar, but last time in that one you replaced 2 chips of different colors by a single chip of the 3rd color. But here we replace them by 2 chips, so the number of chips is not going to change. Find conditions for all chips to become of the same color. Okay, I presume that means conditions for it to be possible. I can check that in a minute. All chips to become of the same color. And there's a little rider to the question. Suppose you have initially 13 white, 15 black, and 17 red chips. So if A equals 13, B equals 15, and C equals 17, can they all become the same color? I'm guessing no, but we'll see. And finally, what states can be reached from these numbers? Ah, okay. I'll just write what states possible. Right, so I want to be more systematic. Let's just think. If we start with A, B, C, so what are the possible things that you can go to? Let's assume, first of all, that these are all strictly positive integers, and then we'll deal with it, because if some of them are 0, that's going to change things a bit. So let's see the possible things that we can go to. So we can either go to A minus 1, B minus 1, C plus 2, or we can go to A minus 1, B plus 2, C minus 1, or we can go to A plus 2, B minus 1, C minus 1. So now the question, or a question that is of interest, is whether we can spot anything apart from the sum that doesn't change. And I have a sort of instinct somehow that mod 3 is going to come in somewhere, but I don't yet see where, because no, I'm beginning to see some hope there. It's because if you look at the first two numbers mod 3, then their sum here subtracts 2, and here it adds 1, and here it adds 1. And, in fact, if you just look at any individual number, in fact, it either subtracts 1 or it adds 2. And subtracting 1 and adding 2 is the same mod 3. So we can say exactly what happens mod 3. So mod 3, one of the numbers is going to, wait, no, all three numbers, in fact. No, beg your pardon. Yeah, all three numbers are going to subtract 1 mod 3. So for them to become all the same color, they're going to have to be the same mod 3 to start with, because if they become the same color, they'll end up being mod 3 the same. And my guess is that that's a sufficient condition as well as a necessary condition, possibly with some edge cases, like, for example, if you start with A00, 0, then we can't take two chips of different colors and replace them by chips of the third color, because there aren't chips of different colors. Let me just check whether it said you start with a positive number of chips, because that might make a difference. No, it just said A white, B black. It didn't say they couldn't be 0. So if you've got two zeros, then you're stuck. If you haven't got two zeros, then the condition, let's just consider the case where you've got 1 0. So we want to ask when they can all become the same color. So that says that A plus B is going to be 1 mod 3. In fact, I'm going to look at an example just to sort of 2 1 0. My guess is that this will work. Oh, sorry, they're not the same mod 3. So what did I mean to say? Smallest example that I can really look at is 3 3 0. Because if I've got a 0, then the other two have to be 0 mod 3. And I don't want two of them to be 0. So let's just see what happens if I play with that one. So I'll take away 1 from the first two and add 1 to the third. And then I've got 2 2 2. One more example where if I had 4 1 1, okay, that's going to go to 3, 0, 3. And that's equivalent to 3, 3, 0, so that'll go to 2, 2, 2. So looking at those rather small examples convinces me that we are going to be able to always going to be able to, as long as we don't have two zeros, we're always, and at the same mod 3, we're always going to be able to get down to the same thing mod 3. And I don't know how much I want to check all of that. 13, 15, 17, notice, are not all the same mod 3, so we cannot get them to become the same color. We know that the sum remains the same, so they've got to add up to 45. And so my guess is that you can get pretty much everything that adds up to 45, as long as this one is 1 mod 3, this one is 0 mod 3, this one is 2 mod 3, but perhaps I should check that. Let me just see if I've got A, B, C, and I want to get to D, E, F. I'd like to find some algorithm. Let's just assume that all these things are fairly large numbers, so I don't have to worry about things becoming 0. So suppose, let's say that A is bigger than D. What might I do to get down to D? Perhaps if I took the two bigger of the numbers, let's suppose that A and B are at least as big as C. So then maybe I would subtract A until I got down to D, and subtract B the same amount. Wait a minute. I don't want B to end up being 0. But I'm not sure whether I'm going to carry on with this, just because it looks a little bit slightly tedious to check that you really can sort of devise an algorithm for getting from one thing to another. Unless perhaps we were to argue that you can first go to some particular triple, and then from that get to your destination. Or to argue that actually is it a reversible process? That's another question to ask. So it's not, perhaps. So supposing I go from A, B, C to A minus 1, B minus 1, C plus 2, and then I subtract 1 from this and 1 from this, and add 2 to this. That'll get me to A plus 1, B minus 2, C plus 1, and then I can do a third one and then get back to where I started. As long as at least one of these things is bigger than 2, is at least 2. But the only way that's not going to be the case would be if I had 1, 1, 0. Let's have a look at that. If I then went to, then I'd have to go to 0, 0, 2. So 1, 1, 0 is not a nice one. That's gets you stuck. And 1, 1, 1. Well, if you've got two ones, then yes, we know that we get two zeros at the end. So the next smallest thing to think about would be, say, 2, 1, 0. But that goes to, then I've got something that's at least as big as 2, so I can afford to do it. So 1, 0, 2 goes to 0, 1. This is 0, 2, 1. And so we go around in a sort of cycle like that. It looks as though we can't break out of that cycle. That's interesting. Of course we can't break out of that cycle because the sum is preserved. So not as interesting as all that. And one last thing, so let's look at 310. Can I get to 040? I probably can get to 040, then I'd be stuck. What would I do? I would just try that. So 310 goes to 202 goes to 131. Not 131, 121, and there we are, goes to 040. That's not quite the same as 400, but it's equivalent to it. But actually, I haven't proved that I could get to 400, so that might be worth having a quick look at. So I had to 310. I had to subtract from those two. And then I had to subtract from those two. But at this point, well, I either had to subtract from, I could have subtracted from any two of these things. So I could have got to 0, 3. No, wait, I could have gone from 0, 1, 3, which would have been this, but in a different permutation. But I always have a 1 in the middle. Oh yes, but that's clearly necessary because it's got to be mod. Oh, something's gone funny there. Oh yes, no, it subtracts 1, but this one's always got to be the odd one out, mod 3. Yeah, so I can get to 040. I think that was my original question, and I can also get to 013. I am going to stop because I've done what I really wanted to do, which was to find the invariant, and I've thought a little bit about what you can get from one thing to another. And actually, these kinds of manipulations here, I think, will demonstrate sort of one can combine these, because if I add all this to some particular triple, then I can sort of do this on top. So in other words, if I've got a plus 2, b plus 1, and c, then I can turn it into a, b plus 2, c plus 1. So I think a combination of those sorts of operations will enable one to prove that you could, what I suggested earlier on, that you could get anything that adds up to 45 and that equals those things mod 3. Right, let's move to another question. I didn't 100% solve it, but I think I sort of got the bit I wanted. So the next question, there's a positive integer in each square of a rectangular table. Oh, I see a table in the sense of something like this, because otherwise tables don't necessarily have squares. So in each of these things you've got some positive integer. In each move, you may double each number in a row, or subtract 1 from each member of a column. Okay, it's another of these processes. Prove that you can reach a table of zeros. That's nice. By a sequence of these permitted zeros. That I find a little bit surprising, actually. But I now want to know what that's got to do with invariance. Because it seems like the opposite of invariance. Usually you use invariance to say that you can't do something, whereas here the question is prove that you can do something. So I think I'm going to have to do a little experiment. So let me draw a nice big 2×3 table just for the fun of it. And let's just put some integers in. 1, 5, 7, 3, 2, 2. I was about to say 6, but let's do 3, 2, 2. So what if I just attempt to so is there something I could do that would be disastrous? I think there is, because if I get down to a 0 in this column, for example, that's actually quite bad news, because say I change that 1 to a 0, then I would never be able to subtract anything from this column ever again, because that number would always be 0. And but that would mean that this I would have to make, well, I couldn't ever make this 0, because I'd never be able to subtract anything from it. So I've got to be very careful not to make 0 prematurely, so to speak. So that's one observation. On the other hand, I do need to get this thing to be smaller, so I'm going to have to subtract something from here. So I think as a first move, I'll double everything in this row. Well, that maybe, so 2, 10, 14. And I'm a bit worried about this 2 here, but perhaps I don't have to worry about it just yet. So let's subtract. Let's just be a bit bold and just subtract until we've got ones, or at some point I've got to, because in order to get zeros, I'm going to need to make the things in the columns, the contributions in the columns, be equal. So on the other hand, if I do that by multiplying all this by quite a lot of stuff, then I've got a quite serious inequality here. So what I could do is actually get this to be equal straight away. So I'm going to double these ones. 2. Actually, I'm not sure there was much point in that, because it's just going to be undone when I do some doubling here. Nevertheless, let's do that doubling. So I'm going to go all the way up to, say, 16. But that's not so great, because I was hoping to subtract from this, but now that I can't subtract 16 from 2. Ah, but I can just make these a bit smaller. So let's take that 2016 down to I'm not even going to worry about it too much. I'll just take it down to, say, 6, 2. I haven't really got a particularly good reason for choosing those numbers, but in this 28, 16, I'll take down, that's a difference of 12, so I'll take it down to 14 and a 2. And now I'll double this again, or maybe I'll multiply it by 4. I don't know whether I'm making significant progress here or not, because that's quite, what number that was? That was 14, so I've got 56. Seems to be getting worse. Okay. So my problem is that this is bigger than this, but those are bigger than that. So I must be able, really ought to be able to do something about that. I somehow want to balance things out a bit more. But how's that going to work? Well, I can obviously make everything in the top row bigger than everything in the bottom row. Ah, so actually that's what I'm going to do. I'm going to make that 8 into a 32. This is not super nice, but 32. So I've got to multiply this by 4, 96. This by 4, that's 224. And now I'll do some, but if I do some subtraction, I don't get to do very much subtraction before this. I'm wondering whether I've made a bad, actually no, because it said I must be able to get to 0 if the question is correct, because it says that from any collection of positive integers you can get down to 0. Let me just check that it did say positive integers. It certainly should have. Yes, there's a positive integer in each square. I'm actually going to leave that example for a second because I want to think about the following question. Supposing I have n, I'm trying to make things as difficult as possible, but in a rather small case. So n1, 1m. So I'm thinking, what am I going to do about this? I can't subtract, but what does it help me to double things? So I suppose another way of putting this question is, what can I do to sort out the fact that I've got this sort of big imbalance, and that when I subtract, I'm in danger of getting a 0 when I don't want a 0. So I can certainly turn that into, let's just multiply everything by 2 to the k or something. And I am probably missing some invariant that's got to be, so maybe there is something where I've got to keep control of some invariant, but I'm not yet noticing. I'll think about that in a moment. So now I can subtract. Perhaps I give myself a bit more flexibility and make that not 2 to the k, but 2 to the l. So my wish to be systematic about these problems has completely, catastrophically failed, but never mind. Oh, that was wrong. I was supposed to multiply the rows by 2. So that should be a k. And that one should be an L. Now, under what circumstances? So if I make L quite a bit bigger than k, then I can organize for these two numbers to be rather more comparable than they were before, but at the cost of making these ones rather less comparable. But actually what I can try to do is subtract just enough from these to get the ratio of these things to be sort of similar to the ratio of these things. So if k, let me just try and get this right. So I don't know whether what I said made sense even to me. So I'm saying if L is bigger than k, we can get 2 to the L. So can get 2 to the L bigger than 2 to the kn, but then 2 to the Lm is much bigger than 2 to the k. But my plan for dealing with this awkward situation is then, so in particular the ratio of 2 to the Lm to 2 to the k is quite a lot bigger than the ratio of 2 to the L to 2 to the k times n. But I can improve this ratio by subtracting 1. So I'm just, yes, had a little thought, but I won't worry about it just yet. So if I subtract something, I can get this ratio to be sort of similar to this one. So supposing I had a situation where I had something more like n an and m am, then I would be in great shape, I think, because I can just double this until it gets to be about the same size as this, and then subtract, and then when I get this down close to 1, I can sort of double it again and get close and subtract, and so on. In fact, I could even just ask myself the question, if I start with just a single pair of numbers, mn, I'm allowed to double one of them or subtract one from each thing. So if I just continually subtract until I get down to, say m is bigger than n to start with, if I go down to m minus n plus 1 and 1, and then I go to m minus n plus 1, 2 to the k, where I choose 2 to the k to be the largest power of 2 that's smaller than m minus n plus 1, or smaller than or equal to. And then I can just keep subtracting, and the top number is always going to get smaller. And that actually sounds interesting. And so it looks to me as though I can do something a little bit similar here. If I got these ratios just being approximately the same, I can then get this to be quite small by just applying this procedure here that I've just talked about, where I, so I'm saying if the ratio between these two things, after I've done some subtraction, is approximately the same, if that ratio is approximately m to n for a different m and n, then I can get it down. I think I want to illustrate that procedure with an actual example, so I won't make it too big. So let's go for 5, 1, 1, 7. I'll write it in matrix form. So then I'll multiply it by something fairly big, I'll multiply one of them by something fairly big and the other one by something less big. So I'll multiply the top one by 8, let's say, so we get 40. A bit more than that. No, I'll stick with that. 48. No, I need more. I'll multiply that one by, what did I, so let me just check what I wanted to do. I want to get 2 to the L to be bigger than 2 to the K N, so I'm going to multiply this by 40, no, a bit more, 50, and so this 7 now becomes 350. But actually let's multiply by a bit more than 50. Let's go up to just some nice big number, 100 and 700. So the ratio between those two numbers is a bit less than 100. I could even go a bit further. I think I want to go even further. So, oh, and I can't multiply by, I've got to multiply by a power of 2. So let's go for 1024. And then whatever 7,024s are, that's 8, 7, 2s are 14, 16, 7168. So the ratio now, is this going to work? It's just under 1,000, and this I can get down by subtracting. I can get down to 1 and then 984, 8, 7168. So the idea what I had here was to get this down by sort of doubling and then doing some subtraction. So I sort of keep doubling until I get near to these numbers and then subtract. But this is not clear, still not clear that I'm going to get down to 0. I'm a bit stumped by this, I have to say. But I also still have the feeling that there is some nice solution that's just waiting to be discovered. I think I'd better go for an even smaller example and see if I can just do it explicitly. So 2113 goes to, I've got to double, otherwise I create a 0, so I'll go for 4213. And I think I'll go for another doubling, so 8413. And maybe I can do some subtraction there, so 8121. Don't know why I decided to do that. And now I'm going to go for 8222. And now let me subtract a bit. So that's 7. No, let's not subtract just yet. Or shall I? I think I want to double again because that 2. Oh no, I don't want to get it bigger than. Okay. If I go to 7111, which is I can do by subtracting 1 from both columns, and then multiply this by 2, I've got this annoying thing where you have this one bigger than this one, but this one bigger than this one. So let me instead double the top 14211 and double the bottom. I'm going to start getting into the same sort of situation that I had here. So how can I improve? Okay, so I will do that. I'll go for 28.4. One 28.422, and then I want somehow to have a thing here being able to subtract more. So 28.4. That's a 28.321. So actually, I think I've done badly earlier on, so I want to go back to 2113. I think I see a sort of possible technique here. So 2113. So I want to balance it. I want to get these ratios a bit better. I keep thinking whether the determinant might be a good idea, but I'll just mention that thought because it's a nice invariant. But so let's go up to 8, 4, 1, 3. And maybe a little bit further. I'll go up to 16, 8, 1, 3. And why did I want to do that? Because if I subtract from here, I can get to 16, 1, 5, 1. And what's improved? Well, maybe nothing too much just yet, but let's just go now to 16, 5, 2, 2. I want to improve the ratio of these things, so I'll get to, so this one's got a ratio of 8, but this one's only got a ratio of 5 over 2, but I can improve that by going from 16 to 4, 1, so I've doubled this ratio. I mean, not doubled it, but I've improved, I've got it up to 4. And now, well, give myself a bit of elbow room, go up to 32, 8. And I'm also going to increase this up to, I'll go to 8, 4. So that ratio is now 4. That ratio is 2, unfortunately. So but I can increase that ratio. So I go to 32, 8, 6, 2. I don't want to go above 4, but I'll go up to 3 there. And maybe 64, I'm going to double everything. 64, 12, 16, 4. So now I've got a ratio of 4 and a ratio of 3. Can I make that into a ratio of 4? No, unfortunately. I can make it into a ratio of 5. But can I then make this into a ratio of 5? Let's just have a go. So 12, 4 becomes 10, 2. And 64, 16, if I were to subtract 4, I'd get 60, 12, which is not a, oh, it is a ratio of 5, 60, 12. And now I'm effectively just got one vector. So it's just 10, 2, whatever I do, I can do an equivalent multiple to the other thing. So if I have 10, 2, I can get it down to, I can get it to 10, 8. And then from there I can go down to 3, 1. From there I can go to 3, 2. And from there I can go to 2, 1. And from there I can go to 2, 2. And from there I can go to 0, 0. So I just copied that on the other side. Whew. So that's my first real success, but what was happening to the determinant? Here at 6 minus 1 is 5. Of course, if I double, that's just going to double the determinant. But maybe if I look at the determinant and divide out by the largest power of 2, perhaps that's a significant thing that I can, except that subtracting something from a column doesn't really have a very obvious effect on a determinant. And then, of course, when we're looking at rectangular matrices, that's also not going to be super easy to talk about determinants. I think that was a sort of a thought that might have something going for it, but is not completely obviously going anywhere. The idea of looking at these ratios and getting them things to be more sort of evened out, that seemed promising, but it's not 100% clear where we can go with it. We'd somehow like to get to a state where all columns were constant. So there's a thought, actually. If we could get to a state where all columns were constant, then we'd be in great shape. And now it's occurring to me that maybe we could do something like that by simply focusing on a pair of values. Supposing I've got a pair of values A, B, and I sort of ignore the rest of the rectangle, which actually I know I can't quite afford to do, but maybe if I choose things in the right order, I'll be able to afford to. I ignore the rest of the rectangle. I have a sort of proposed method for turning A, B into two things that are the same. And the rough idea is that you take whichever is bigger, you subtract until B is 1, and then you multiply by 2 repeatedly. Actually, you don't even have to do that. Here's how we could do it. So I'll give you an example. So say I had 15, 6 or something. So I keep subtracting until I get down to 9, 1. Sorry, I have to subtract 5, so 10, 1. Then I double the bottom thing, and so it'll be 10, 2. Then I'll subtract again, so that'll be 9, 1. Then I'll double, and I'll get 9, 2. And I'll subtract 8, 1, and so on. So I can get down to 1, 1 without any trouble. Now, in the process of doing that, am I going to mess up anything else? Well, if A was bigger than B, then all I did during this process was subtract things from up here. I subtracted B from everything in this row, and then I kept subtracting A until I kept subtracting 1 from A until I got down to 1. So roughly speaking, I subtracted A plus B from everything up here. So what I'm thinking is if I make A and B be, if I sort of pick the smallest things to play with, or perhaps if I start by, but actually now if I want to do the same thing over here and I've made these equal, I'm going to have to worry about whether I make them unequal again afterwards, so that's not so good. But there is a useful insight here, which is no, or is there? Now, what I was about to say was, but I saw immediately that it was wrong. I sort of wanted to make sure that those were equal, then that those were equal, and then that those, but if I've made those equal, I can't then change that to make it equal to this and then hope that it's still equal to this. I can only do that if things start going down. is there some process one can envisage that, let's say, reduces the sum? Obviously not in one move, because when you double everything in a row, that's definitely going to increase the sum. But is there some process that one could do that says, or maybe reduces the maximum element or something like that? That seems somewhat complicated as well. I'm feeling fairly stuck. So what possible invariants could there be? That ought to be something one could think about. So I want something that doesn't change if you subtract 1 from everything in a column. And if you multiply everything in a row by 2, that is very strange. It doesn't seem as though there's anything obvious with that property. So I think my next thought is, can I build up from this idea that solves the problem in the case of a 1 by 2 rectangle? And let me just have a think about that. So if I start, again, I'll sort of go for sort of 1, 5, 7, 1. That's not the same as an example I've already looked at, is it? No, I don't think it is. That's designed to be a slightly troublesome example, but not very. So what I did in the case of a 1 by or a 2 by 1 matrix was subtract the smaller one from the bigger one repeatedly, and which I did by doubling it and then doing a subtraction. So actually that's a little point to note. So if I've got a row x and a row y, then as long as y is smaller than x in all coordinates, then I've got the option of doubling y and then doing a subtraction. So I can always go to x minus y. So I can subtract a row from another row. So how do I do that? As I say, I double y, and then in each column, so I'll just do it here. So this is not smaller than this, but if I double it enough times, I can get to 8, 40, 7, 1. Now I claim I can, if I want to, I can subtract this row from this row. And the way I would do it is to double this row. That would get me 14, 2. 8, 40, 14, 2, and then I can subtract 7 from this column and 1 from this column, and then I'll get down to 1, 7, 39, 1, and sure enough I've subtracted this row from this row. Not exactly a better position than I was before, because here I had 1, 5, 7, 1, but I'm not claiming that that's going to be better necessarily. But what I want to do is use that as just an extra operation that I have available if I want it. So there's still the question of how I've managed to do this, so I know it's possible. The question of how we avoid a situation where we have two small ones on one diagonal and two big ones on another diagonal. So what was there's some trick that enables us to get these. So there's a sort of ratio of 1/7 and a ratio of 5, which is not a very nice situation to be in at all. But if we multiply this by something big, then we've got two ratios that are quite close to 1. And what can we do in that situation that sort of eventually gets us down to a good situation? So let's just, supposing I turn it into 2 to the k and 5 times 2 to the k, and I've still got 7, 1 here. How can I, so this is smaller than this, and at the moment I'm always subtracting something that's smaller. But that I can certainly deal with. I could go to 2 to the k, 5 times 2 to the k, 7 times, well, let's multiply by 4 or something, just for the sake of example, 28, 4. And then I can subtract a whole lot of stuff from here and get it down to 1, and it'll be 2 to the k minus goes up to 28, so minus 27. And this ratio will still be about 5, and here we've got a ratio of 1 to 4. So now I can sort of start subtracting this from this several times and get it down to something that's quite a lot more manageable. But towards the end, this ratio that's about 1 to 5 will become worse than 1 to 5. So is there something else that I can do that will subtract more? Yes, I can always sort of, as it's coming down, I can always double that and then subtract 1. And that's sort of interesting. Then I can be subtracting a different number from these things each time. What does happen to the determinant if I subtract 1 from each? So if I've got AD minus BC, it'll go to, if I subtract, so this is for a matrix A, B, C, D, let's say. If I subtract 1 from B and D, it'll go to A, D minus 1 minus B minus 1, C, which equals AD minus BC minus A plus C. So the determinant will go down if A is greater than C. But that is, we also know that the determinant doubles if we multiply a row by 2, but if we always we also know that if we do a row operation on this thing, then so if I replace AB by A minus C, B minus D, that will not affect the determinant. So can we get to a stage? Could we just multiply everything by something quite big, some fairly big power of 2, and then just argue that we can do some row operations? But we still have the problem we have to keep everything positive. But so here's a sort of basic idea. What if I multiply the 1 and 5 by something really large, and then try and do it by a combination of subtracting 1 so I get to this stage here, 2 to the k, 5 times 2 to the k. And the operations I'm allowing myself are row operations which don't affect the determinant, and subtracting 1 from a column, which, as long as this number is bigger than this number, will reduce the determinant. But the question is how long I can carry on doing that for. Without making a 0 when I didn't want it. And that still doesn't seem to have a very satisfactory answer. I'm aware that I've gone on for a very long time on just this one question, which may not be extremely interesting. And I think I'm just going to have to, I mean, I will think about this, but I hope I'll manage to solve it at some point. But annoyingly, it has defeated me for now. But in the spirit of, I don't know what, I will put it up, but with a warning that it may not be super interesting to watch. And if you manage to see what I have not managed to see, then I hope you get some satisfaction out of that. And I will stop recording.